We're talking about something called the value improvement path today, and basically how we can use that to improve convergence properties of reinforcement learning algorithms. So in order to get started with this, we're firstly going to say that this paper contributes in a number of ways to the existing literature. So namely, they propose a new formulation of the representation learning problem in terms of the value improvement path. And the representation learning problem, which we'll get into in more detail in the next slide, has to do with automatic discovery of representations needed for feature detection. So as we're doing reinforcement learning, we need to detect features, and in order to do that, we need some sort of representation of our environment. We're gonna, as I said, go into a bit more detail in just a second, but we need that representation to be adequate in order for us to learn effectively, and that's what the representation learning problem addresses. And in addition to this, the paper gives an interpretation of auxiliary tasks. So auxiliary tasks are extra tasks or additional tasks that you can add to your environment in order to improve learning rates or convergence properties of your algorithm. And the paper, so this is something that's been proposed before. This is nothing new, but what this paper does that is new is it gives an interpretation of auxiliary tasks to address the representation learning problem specifically. And also it gives two novel auxiliary tasks inspired by value improvement path, and they demonstrate excellent performance on the Atari suite of games, which is what this paper was tested on. So let's have a look in more detail now. Basically to give an account for the features and what we're trying to do with the representation learning problem, we need to consider what we do in reinforcement learning in general. So we try to estimate an action value function in general, so a Q value function. We indicate our estimate with Q hat pi, and we can parameterize this according to some inner product between a set of features and a set of parameters. This is quite common parameterization of a Q value function. And as I said, the phi is what we call the features, and the theta here is a parameter vector. And if you know some linear algebra or just see this expression, you can see that phi basically dictates the span of our space. So it gives us the range of Q value functions that we could potentially get, and the parameter values constrain this space to give us a particular action value function. And so the representation of phi is going to have an importance for what space we are actually considering at any given point in time. And the representation learning problem is the problem of constructing these basis functions phi in an adequate way. We want to also have a look at what's called the value improvement path now, which tells us something about how action value functions improve throughout the learning process in general. So on the side here, we can see an illustration of the value improvement path. The first thing to note is that up here, we have the optimal action value function Q star. Down at the bottom here, we can see basically our starting point for the evaluation. So this is some initial seed estimate of our action value function. And what we do in general with reinforcement learning is we iterate this to approach the optimal action value function. So we would traverse this space of action value functions in some order. The particular one that we consider in this example is highlighted in red here, and then we would make it toward the optimal action value function at the top. And this gives us a path across a space of value functions. And this path that we take is called the value improvement path. And the thing about this previous slide that we talked about, so namely the feature space phi, is that we want to tailor phi to give good approximations of the action value functions that we have. But we don't want to over-specialize it to any given one of these action value functions, because let's say you over-specialize your feature space to this particular one. We know for a fact that the action value function that we're estimating right now is not the optimal action value function. That's where we actually want to get to. And so we need to be able to generalize the feature space to also cover the action value functions that we want to attain. The problem is, of course, that we don't have those functions as of now. So we want some sort of intermediary where we optimize the feature space to adequately represent our current action value function, but also take into account what we perceive as being likely to come our way in the future. And that's what the paper tries to address. So we're going to have a look at a theorem now that tells us basically how we can limit the error of any given estimation over long periods of time. So basically the convergence properties for our algorithms. And what we want to consider is a policy pi and a distribution of a state action pairs d mu and a representation phi. So we have these prerequisites, and then we suppose that policy iteration's approximate value path is well approximated in the sense that for some epsilon bigger than 0 and related distributions, this property holds. What this property tells us is that the distance, so I mean, if we just look at this, we have the distance here between Q, which is the action value function. And then the other term in this, expression here is the projection of Q onto the set of feature vectors. So the space spanned by the feature vectors, Q projected onto that space. So this pi here indicates a projection, basically. That's the notation for it. So the difference here is the difference between the projected Q and the Q itself. And so if this difference is small, that basically means that our feature space spans the action value function in a good way. If the distance is large, that means that we're not really spanning it. So there's a big difference between the space that we can represent with our features and then the actual action value function that we're trying to approximate. So we say that basically for all Q functions in our action value path and for all iterations K, we have a limited error here, and it's limited by the number epsilon. Those are the prerequisites. And what this now tells us is it gives us an upper estimate for basically where we're going to converge, or how close we can get to the optimal action value function. So if we read the second part of the theorem, it says that then for pi k, representing the kth approximate policy iteration starting with pi 0 equals pi, we have, and then lim sup of basically the magnitude of the difference here. And this one is slightly different, right? So we can see that here we have the optimal action value function. This is what we want to converge to. And then we have the approximate action value function at some given time step, so time step k. And we say that as k tends to infinity here, this error, so the projection error between the optimal action value function and the estimate that we actually produce, is going to be limited by this term here. And we can see that gamma here is the discount factor of our particular reinforcement learning algorithm. But the key thing to note here is epsilon is included here as well. So if you can make epsilon very small here, you're going to basically limit the error as you converge, or as k tends to infinity. So it gives you an upper bound for how good of an approximation you're going to make. So this is a quite strong theorem. And what it tells us in practice is that if we have a good way of representing the action value function within our space of features, then we're going to have very good conditions for actually converging over the long term. So that's an important theorem, and we need to keep that in mind going forward when we discuss the strategies laid forward by this paper. So next, we're going to have a talk about pseudo rewards, or cumulants, which are a way of shaping the value improvement path according to our liking. So as we said briefly in the beginning, these rewards are additional rewards that you can produce, and they're not strictly related to the environment, or they're not, let's say, intrinsic properties of the environment from the start, but they're rather something you add in order to get better convergence properties. And these additional tasks help shape the representation phi and can help limit overfitting. So one thing about adding these tasks is that you're kind of distorting the actual reward because you're adding some additional reward that's not the one you want to actually maximize in the end. So the gut feeling is that including these would probably lower the performance, right? Or introduce noise into the process. And this is the case if phi is infinite. So if the magnitude of phi, that is the space itself. So if you can already represent everything with your feature space, then adding any auxiliary tasks are only going to noise the reward signal and basically lead to, well, poor or like worse convergence. However, when phi is finite, you have a trade-off because partly, sure, you're noising the signal, but these phi values can actually help you align the representations in a better way. And so therefore you have this trade-off where if you can construct these auxiliary tasks in a good way, you might be able to actually increase performance. And that's exactly what they're trying to do with this paper. So we're going to illustrate now exactly what they're doing with the different methods that they're investigating. And first of all, we're just going to have a look at the value improvement path to basically get a sense for this illustration. So they plot everything in a plane here, and this is the span of the polytype that constrains the Q-value functions. So all Q-value functions that we can get are basically contained within this space, which they represent as a plane in this figure. What we can see as well is that this line that goes through it shows the value improvement path. So at the top here, we can see the optimal action value function, and at the bottom, we can see basically our starting point. And as we iterate with our reinforcement learning algorithm, we're going to traverse this path and get closer and closer to the optimal action value function. And we want to do this as efficiently as possible. And it what we want to answer is basically how well do the representations from different auxiliary tasks span this value improvement path? That's one fundamental question, because if we add these auxiliary tasks, we want them to basically help us traverse this path. And so the way we would do that, so in order to be able to traverse this path, we need to basically span those values with our feature space, right? So this is not the feature space itself, but as I said, it's the polytype of actual action value functions. So these are where the action value functions reside, but they're not necessarily what we can approximate using our feature vectors. And we want to align our feature space with this space in order to be able to approximate them well. And so that's what we want to resolve with the auxiliary tasks. What we can see is if we only use the value function of a particular, action value function to evaluate these feature vectors or the span of feature vectors, they might not align well with the actual polytype. So as you can see here, we have a subspace phi, which is where our feature space resides. And in this particular case, if we don't have any preference for how we train the algorithm, it might end up so that this span is, let's say, orthogonal to the actual space of action value functions. Now, if we think about the implications of this, this would be quite bad for training purposes, because let's say you train an algorithm and you get this space of feature vectors. If you remember the inner product that we discussed in the beginning, we basically said that the approximate action value functions that we can generate are going to be the inner product between the feature vectors and then some parameters, which means that we're always going to be somewhere on this line with the next approximation. So we actually want to move in this direction, right? But regardless of what we select in this feature space, we're not really going to get closer, which is a problem. So what we want to do is we want to align this subspace with the actual hull or the actual span of these action value functions. And that's what we can use auxiliary functions for. So we cannot just use auxiliary functions, let's say arbitrarily, because that wouldn't really help us either. And that's what this figure here represents. So if we add these auxiliary tasks, they're not necessarily in the same plane as the action value functions. And so if they're scattered all over the place like this, sure, they would influence basically the span of our feature space phi. As you can see, the line here is a bit different from before, but it's still not very well aligned with the path that we want to traverse here. So just adding arbitrary auxiliary tasks aren't getting us anywhere. What we can do instead is to actually restrict these points to belong to the same space as we can actually obtain with our action value functions. In order to do this, we need to first understand why do they diverge from this plane in the first place. And to realize why, we got to think about what happens when we introduce these auxiliary tasks. When we introduce them, we basically add rewards to our environment. And in doing so, we change the environment that we're in. So the environment is not agnostic to the rewards that you get, but they will actually influence both the environment, but then also the action value functions that you learn. So the action value functions that we get out from this are not going to be necessarily the same as those that are possible from just learning from the rewards of the standard environment. And that's why they don't really belong to the same space here. We can, however, restrict them if we ensure that the auxiliary tasks that we use in some way come from the space that we want to end up in. Now, how do we do that? The answer is something called cumulant policies, or one answer to that problem is cumulant policies. What we do there is we learn qi, so you can notice the subscript I here, and we have another q here, which does not have the subscript I. The difference between these two, so let's start with the difference between them. The difference between these two is that the one with the subscript is the action value function evaluated on the auxiliary task itself. So you introduce the reward and then you train your action value function on that, and this is the one that you're getting. And also associated with that is you have some policy, right? Pi I. So the policy associated with cumulant function I. And as I said, this action value function is what you get from evaluating that policy pi I on that altered space with the auxiliary tasks in it. The other one here is using the same policy. So you can see that it's pi hat I. So the one that you get from basically taking the auxiliary task into account. But this one is actually evaluated on the standard environment, so the original environment. And therefore, this one is going to be in the subspace. And that's what we use as an auxiliary task for that particular reason, because we now use sort of the policy that we learned earlier, but we evaluate a q-value function based on that. And this q-value function we know is going to be in the space because it comes from the exact rewards that are associated with the space that we're interested in. And so that's the way I restricted them to the plane here. Of course, these points are going to be sensitive to the policies that we get. So the various i's that we get from our auxiliary tasks. And therefore, it's not going to be, let's say, stable to all kinds of auxiliary tasks, but it's very dependent on what those tasks are. And one additional thing to note is that this space is often very big. So this represents all the Q value functions that we could potentially get. The ones that we're actually going to end up traversing on the way to the optimal action value function is going to be a subspace that's a lot smaller than the space itself. And so there's plenty of reason to believe that this space phi, or the subspace phi here, might not actually align with the value path that we want to take, even though it's in the same plane. So this is not a perfect method by any means. And that particular problem is something the authors are trying to address with the two novel approaches that they're proposing now, which we will now actually start discussing. So these are called past policies and past mixtures. And the difference between these and what we discussed just before is that these take into account the previous action value functions that we've actually seen. So the fundamental assumption that they're making, and which kind of lays the foundation for this method, is that the past action value functions here are going to align quite well with the trajectory that we want to follow going forward. So in this image, we can see that it does a pretty good job, right? Because the action value path seems to be going in a certain direction and doesn't do a lot of crazy stuff. And we use these auxiliary tasks then from the previous action value functions to get our space, so basically our phi. But you could imagine if this trajectory now veers off, let's say like 90 degrees in some direction, this might not be a good approximation anymore. So it's still dependent on the environment, but the authors are making the claim that in general, we believe that the action value functions will have some sort of trajectory that they tend to follow. And if they do so to a large extent, then this is going to be a very effective approach of basically getting to the optimal action value function. There is a second proposal then. So the past policies suggest that you use action value functions from the previous K action value functions that you got in your value improvement path, and K is some fixed number. And then you also have past mixtures, which is a mixture of the different auxiliary tasks that we can have, where you would implement it by having different learning rates for the different auxiliary tasks and then using their average as your bootstrap target. So the mixtures is sort of similar to the past policies, and the only difference is really in how we mangle together the past information that we already attained. But the general principle is the same. We look at the past action value functions that we attain to make some prediction about where we think the value improvement path is going in the future. We're going to go ahead now and look at some actual results that they found during the study that they did. And the first thing we're going to look at is something called the generalization error. So remember, the purpose of what we're trying to do is we're trying to come up with a set of arriving at features, and those features need to generalize well across action value functions for the entire value improvement path. And how well this is performed on the arcade environment, so this is the Atari suite of games, is illustrated by the figure here. So what we can see on the x-axis is the time difference between the current action value function and then the future action value function. And here we basically see the mean squared error. So the lower the MSE, of course, the better the approximation of action value functions is going to be. So for the negative values here, we're basically comparing or trying to estimate previous action value functions. So this is not really what we're interested in, but it's good for getting an overview of how these models perform. The future, however, can be found on the right-hand side. So these are time steps into the future. And this is what we're really interested in, right? So we want a model that can generalize well across future action value functions so that we can converge to the optimal action value function in a better way. And what we can see here is basically the various methods that we've been discussing in previous slides are in this graph. And the best performing one is the past mixture. And we can see that the past policies is also performing very well on the generalization error. We can see that the standard double DQN algorithm, which is the underlying algorithm of all these, is performing worst of these, especially, or at least after we exceed, let's say, 7 time steps or so. So this is quite an interesting result. And we can see that even on the past policies and past mixtures generalize well. And this is what we would really expect, right? Because we're in fact using the past action value functions to generate our auxiliary tasks. So we would expect them to definitely generalize well in this direction. But the thing to really note is that even for the future time points, they generalize well, at least in the Atari setting. So it's very hard to draw any firm conclusions on how this would work on any given situation that we place the algorithm in. However, the Atari suite is quite general in the games that it encompasses. So I would say there's a good level of variance within that set. The next thing we want to look at is basically the long-term performance. So we have the figure from the last slide here, and we have two additional ones which show the mean performance and then the median performance for all of these. So the color coding coincides, right? And the thing to note, or the reason why I have the generalization error graph in the same figure here, is basically we can see a strong alignment here between a low MSE on this graph and then a high performance here. Now, note that these are not performance metrics per se, they're generalization metrics. So they tell us how well the action value function, or how well the feature representation rather, generalizes across action value functions. And if you remember the theorem that we discussed in the beginning, we basically said that if we can encompass the action value function well within our feature space, that would basically allow us to converge better over the long term toward the optimal action value function. And this is exactly what we're observing, or at least what we're seeing an indication of here, right? So we have good generalization, which means that probably we're quite good at containing the action value functions within our feature space. And the result of that is that the performance over the long term tends to be quite good. So this is really a strong result. And both of these novel approaches that were new are basically outperforming whatever was state of the art before. So this is really a finding that's quite useful. And it stresses the point that the thing we want to ensure is not that we optimize on the current action value function, but that we really take into account the full trajectory of action value functions that we're going to traverse on the way to the optimal one. So that's the main conclusion of this paper. And I just want to thank you all for having a look at the video. I hope to see you in the next one, and take care in the meanwhile.